I'm tasked with introducing Marc D'Antonio. And it's all about inflection, right? Marc D'Antonio is an accomplished astronomer, researcher, and the chief photo video analyst for MUFON.
You can tell we know each other.
Yeah. Now, we've known each other for quite some time now, and I keep telling Marc that we're just going to roast him up here. But he's going to return the favor tomorrow when me and Stan are speaking. So, Stan's right there. So we are the Paranormal Rangers, and it's my pleasure to introduce Marc to you, as you already know him. And he's going to talk about a bunch of wibbly wobbly, timey-wimey stuff today. So hold on to your seats. Here he is.
Thank you, Jonathan Dover, and thank you, Stanley Milford. By the way, pick up Stan's book, Paranormal Ranger. Fantastic. Do you have them with you? Oh, okay. Well, anyway, I tried. Anyway, yeah, as I said yesterday, I'm Marc D'Antonio. I'm an astronomer. This is how we look. You can see my SkyTour live stream shirt, and if you look on the back, you'll notice that Pluto is listed as one of the planets. Damn right. All right. Now, I've differed with the International Astronomical Union on whether Pluto is really a planet or not. And I say it is, and I have lots of reasons why. It orbits the sun independently like other planets, but it's at a slight angle to our plane of our solar system. But it has its own moons. It has 5 of them. And there's no real other objects out there beyond Pluto that have 5 moons. There's binary asteroids that kind of go around each other, but there's nothing that has its own moons. So Pluto, planet. Yeah. And if you want one of these shirts, by the way, we do sell them. We are a 501c3 nonprofit with the remote observatories. No, you're not a captive audience. I'm just making the announcement. So if you want to go to skytourlive.org, you can go and talk to me. You can also connect with me. SkyTour is free, and all the images we take are free. You can download them from our portal. We have 4 years or more of photos that we've taken with our remote observatories out in the Arizona desert, which I run from Connecticut, where I live. All right? So I developed a lot of technology to do this, and because I can do that, I figure why not give this stuff away? Because education shouldn't cost you a dime. And science should be free for everyone, and I think everyone should be in that discussion. Agree? Yeah, of course you do. Of course. So today we're going to talk about something that, it's the linchpin, okay? We talk about UFOs, and you get guys like Neil deGrasse Tyson, who follows me on LinkedIn, by the way, and he'll say things like, well, I don't believe aliens are here. No, they're a vast universe. How could they possibly get here, right? Then when Neil deGrasse Tyson starts following me and others like me, he's asked that question again, because that was like a 5-year-old or a 10-year-old answer from him. Now he answers this way, well, we need more data. That's a win, because when a guy like that, who is very, very definitively academic, all right, starts to say things like that, he's starting to soften, and that works well. Who's heard of Avi Loeb at Harvard? Okay, he's the chief of astrophysics head, chair of the astrophysics department at Harvard. I've worked with him a couple times on a few shows. All right, now Avi says things like, I believe that this 3i Atlas object that's just entering our solar system, almost on the plane of our solar system, he says, we can't deny the possibility that it might be an alien probe. He didn't say it is an alien probe, but the news only heard alien and said, Avi said it's a probe. And that really hurts the discussion. We want to find out what this thing is. Right now, from all the data I've seen, the chemical analysis, the spectra, it looks like a comet, like the one before it that came in. Okay, the first one was 1 with a little I, and that means 1 interstellar, and then Oumuamua, remember that? Okay, people in the press reported it as being a long spindle thing, and that was wrong. it was a pancake-shaped thing. Avi said that from the start, but the press only heard thin and long. They didn't. That was from the cross-section from the side. Okay, they didn't look at it from this side to actually see there was a round pancake. So anyway, you got to be careful and be critically thinking about the information that you're getting from the press. Very, very important. So that said, and if that cover stays on, maybe we'll actually be able to use this monitor. What happened was one eye Oumuamua came and went, and we saw it after it left our solar system. How do we know it was an interstellar object? Does anybody actually know the answer to that? Okay, I'll tell you. An object that comes in from the outer cometary belt, where we see that we call it the realm of the comets. It's called the Oort cloud, okay, that surrounds our whole solar system, a big spherical collection of icy bodies. If one is dislodged somehow by gravitational interaction with a passing nearby star, and you can tell this takes hundreds of thousands, if not millions of years to occur, it might make its way on a circuitous path to come into the inner solar system. But when it does that, it can only reach a certain speed and no faster, because from out there, there's only a certain amount of speed it can gather when it comes into the inner solar system, okay? These interstellar objects that they're calling interstellar are coming in at way more speed than the objects from the outer belt, the outer sphere of material that we're talking about. So that's how we know they're interstellar, because of their speed generally. This one's different. 3I Atlas, okay, no, well, there was 2I Borisov, and that was a comet that came through. Again, high speed, we knew it was a comet from that. 3I Atlas is actually what looks like a comet again, but it's coming in now at the plane of our solar system. Very strange, very unexpected. So it's also doing something else strange, and the percentage chance this is happening is like 0.002%, okay? It's going to visit Jupiter, then it's going to visit Mars, then it's going to visit Venus on the way out. The chances of that happening in this dust bowl that's become this room, but that's okay. I mean, we need the air. It's air or dust. Make your choice. The 3I Atlas coming in at that level seems to be a very interesting trajectory, something that wasn't expected. And so that's where it is right now. It's an interstellar comet that has a strange orbit. But that's conventionally coming into our solar system. It's coming in at a high speed. It's going to gravitationally whip around the sun and leave, okay? That's all happening in our 4 dimensions, X, Y, and Z moving through time, all right? This talk is about things that may not work and take place, well, their motion may not take place in X, Y, Z moving through time. It might occur in another way. And we're actually seeing hints of this possibility with physics. And you're going to learn about this and be able to walk away and talk about it. And I'll tell you why, because I'm not going to put up equations. I'm not going to make you solve differential equations through calculus. I'm not going to make you do any of that. You're just going to learn the concepts and understand what's going on in the physics world that will allow you to walk out of here saying, wow, they really can be here, and it isn't that difficult. And that's going to prompt you to think about why there's so many different civilizations that could possibly be seeing us right now. So, without further ado, okay, we're going to start with early astronomy, all right? When we look at early astronomy, we see that there were stone tablets. Okay, we had 17,000 years ago, we had cave paintings of stars and constellations. Then, of course, 3000 BC, we had Mesopotamian stone tablets. And then we had the Babylonian tablets, 1000 BC. And all the data was pecked on these little tablets. And it recorded constellations and star positions. And why? Well, because they equated the stars with their deities, as you've heard multiple times while here already. Not from me, but other people. And so when the early Greeks got a hold of astronomy, they decided, as an ingenious civilization that they were going to create metallic measurement devices. This one is called an astrolabe. It's actually, and the laser doesn't work, but that's okay. This astrolabe is a brass astrolabe, and it would help measure positions very accurately, the stars in the sky. All right? So astronomy was a young science for a long time, and when it matured, it started to become more and more accurate, and some of the discoveries that were made were more and more incredible. Now, in 1054 AD, the Chinese astronomers saw this most incredible object in the sky, and it was another star. This other star was seen in daytime, all right? And this daytime star was so bright that even with the sun out, you could clearly see this in the sky. So that's a very, very bright object. What was it? It was a remnant of a star that blew up, and here it is. This is called the Crab Nebula. In 1700s, Charles Messier cataloged it as the first object that he observed, Messier 1. And Messier 1 became the very first of 100 and some odd objects that were in his Messier catalog of objects to avoid when looking for comets. Yeah, he didn't like this stuff. He just wanted to look for comets. All right. So later on, okay, the first telescopes to see it were in the 1700s, and those telescopes were made by, one of them was made by William Herschel. It was a 43-inch diameter mirror made of a metal called speculum metal, believe it or not. And it was metal that would tarnish within minutes. So he'd make an observation, and his sister, okay, they would swap positions. His sister would go down and polish this metal mirror until it was nice and shiny, step out of the way, and let him make his observations and drawings and write stuff. And then she would go back, okay, polish it again, Claire or whatever, I think it was Claire. And so she would polish it again and thus make this incredible mirror shine bright again, and then he could observe for a little longer. It was crazy. Now, that telescope was very cumbersome, but we started to refine telescopes. I actually worked for 4 years in an observatory, much like that one on the lower right, with a very, very large refracting type telescope. It was so large, in fact, that the entire building's floor, a big round 48 feet in diameter floor, would move up and down, and it's an elevator to meet the telescope. So many times when I was working, I'd bring friends in, and they didn't know that. So I'd set the telescope on an object, and the eyepiece was way up there. And they're like, well, how are we going to see the eyepiece? Oh, I'll show you. And I would turn the elevator, and boom, the whole floor would go up, and they would go, whoa. And they would enjoy that. So then now suddenly the eyepiece is right here. And you held it in your hands, and it was so big you could use 2 eyes to look at the object, like binoculars, except all the light's getting to both eyes. It's crazy. So that was very, very important to develop these types of telescopes. Now, later on, we developed a 200-inch telescope at Mount Palomar, okay? And this telescope, in the early days, you actually sat inside this here. This was the observer's cage, it was called. And this is the telescope here, and then this is the mount that would, rotate left and right, okay? All right, and then this part would go up and down. So it would rotate left and right, and then the inner part would go up and down, so you can get to the different places in the sky. When you are in an observatory, and I can vouch for this, you can't heat the building because you have to be at the same temperature as the outside air. Otherwise, the slot will have this warm air percolating out of it, and your images are going to go like, bleh. So you're not going to get a clear image of anything, right? He's smiling. He seems to know, okay? Yeah. So the point is that the telescopes have to stay at the same temperature as the outside air. Many a day, I've worked in a telescope dome where the temperature was 10 below zero. And I had to be able to handle delicate equipment, so I couldn't wear gloves. So I'd have gloves until I needed to use this equipment. I would grab this metallic knobs and things that it's like, oh, so cold, it was outrageous, So we moved on, and now we remoted a lot of things. These are the Keck telescopes on Mauna Kea in Hawaii. These are 33-foot diameter telescopes, and they work in tandem. They can work singly, but they also work in tandem, like 2 big eyes, one in each, like each eye socket. And these telescopes can observe the heavens, and they also can account for turbulence in the atmosphere. It's called adaptive optics. So as the light comes in, they're made of multiple mirror segments, and then each mirror can vibrate and move a little bit to make the light coming to the telescope a little bit sharper for each mirror segment. And by the time it gets to the main focus point, it's a much more sharp and clear image overall. So adaptive optics is very important. All right? So we made some strides, in other words. Now, along the way, we had to get off the Earth, and we did that by getting to something called the Spitzer Space Telescope, kind of the second entry. There was one before it. But this was a telescope that looked in the infrared. It looked from, if you remember my analogy yesterday, we have red, orange, yellow, green, blue, indigo, and violet. This is the visible spectrum, right? So that's what we see with our eyes. The Spitzer couldn't see that, just like James Webb. James Webb sees all the way to the edge of the tent in the infrared. The Spitzer Space Telescope was about here. Okay, so it was sort of, if this is the end of the red, the infrared started here, and this is about where the Spitzer could see. It couldn't see far into the infrared. But nevertheless, it showed us some incredible vistas. And these are galaxies and nebulae that we never saw in this light before. And only from space can you see this. The atmosphere very efficiently blocks infrared energy. Although you go outside and say, but I'm so hot. That's ultraviolet energy heating your skin, okay? It's not infrared energy. That's what's radiating off you and making you feel warm, okay? So along the way, after we did that, we ended up making the Hubble Space Telescope, which was fantastic. It showed us incredible vistas like this. This is an image of the pillars of creation. Who's heard of that before? Right, and Hubble popularized it. We take photos like this of the pillars of creation all the time with one of our remote telescopes, the one in Benson, Arizona, because it's a narrow field shot. And it's just a little larger size than this. But we're at 3,600 feet in elevation on a mountain with other professional astronomers. So at 3,600 feet, you're not 400 miles up in a telescope in space without atmosphere. So we don't get shots that look as good as this, but they look good nonetheless, right? It's the best we can do. So this is a visible light image on the left side, and on the right side is an infrared image of the same region. What's the difference? What do you notice right away? Anybody? More stars. Exactly right. And that's because you may not realize it, but all the stuff in here is dark dust that's obscuring the stars behind it. All right? And it's in that dark dust, which I said to you yesterday, I kind of alluded to, that's where life begins, in the dark. And I made a joke about, but life begins in the dark, and that dark dust is where all the chemical soup is manufactured and made, and where all the ice and all the other compounds and chemicals and elements and molecules can exist in there that become material from which planets are made. And there's lots of hydrogen in there, the most abundant element in the whole universe, right? And it's in that region where that hydrogen can form a star, and the other slurry of materials around it can start a disk and make planets, just like here. It's called the nebular hypothesis. Now, that is a very interesting discovery, that there were more stars hiding in the background. Until we went into the infrared, we never knew this. Now, that means if we're seeing that many stars, is there that much more life, possibly? And the answer is resoundingly, yeah. Right? So, we figured, what? Since there's so many stars, we're going to start looking for other worlds. And we used the Kepler Space Telescope to do that. Now, Kepler was very interesting. It worked for quite a while. And it steered itself around by using things called reaction control wheels. Now, I worked on a satellite in Gilbert, Arizona, and my task was to build an engineering model of it. I have an independent company, a model-making company. I do a lot of work for the Navy, as I think I told you. And so the model had a lot of top secret stuff on it, all right? So you had to be someone who had a high clearance to be able to work on it, so they said, oh, he can do it. So I flew to Gilbert, Arizona from Connecticut once a month, and I stayed a couple days, worked in the high bay of this satellite place, and took photos of this satellite, all right, that was being built. And I was going to incorporate what I saw into the model. All right, well, so I learned about reaction control wheels there, and there's 4 of them on these satellites, 4 on Kepler, and there were 4 on this other satellite. Kepler, as long as it had 3 of these wheels, and what they are is they're little weights that are spinning, okay, in a little disc, and they like hard drives, okay, and they were spinning, and as they spun at a certain rate, they would impart what's called a torque, an angle. The telescope. It was for positioning the telescope in a very, very accurate manner. And as long as it had 3 and it had 1 extra, then those 3 could handle the positioning of the telescope. Problem was, it lost 2. And so they had to come up with a new idea. The new idea was to let the pressure of the sunlight, the solar wind, which are protons and electrons streaming at you from the sun, let the pressure of those little tiny masses overall add up to a force, and then they countered it with the other reaction control wheels so they could use that sun's pressure to re-steer the telescope. That was ingenious, and it ended up making K2, the next successor to Kepler, and they found thousands of planets. And by the way, the area in the sky that they were looking at was a fist size over your head. If it was miraculously clear tonight, I could show you. It's in the constellation of Cygnus the Swan, I think what you heard about earlier today. Okay, and Cygnus is that size area overhead is where they found many of these planets. It's incredible. Now, the planets they found are numerous and incredible. Some are big gas giants. Some are kind of like the Earth, but we can't really tell. All right? And in a few short years, what we discovered was so many planets. It literally, the number we had discovered simply doubled with just using the Hubble Space Telescope. Now, in addition to the Hubble Space Telescope, we ended up using TESS, the Transiting Exoplanet Survey Satellite. Now, TESS was special. TESS actually looked at an area that was 24 degrees by 96 degrees in size. Kepler was like a laser. It would look at one object at a time, one star, bink, study it. And what it was looking for was planets that might be passing in front of the shape of the star. Right? If it passed in front of the disk of the star, we can't see the disk of the star. It's too far away. But if we could look and see when a planet passes in front of the star, the light will actually dip a little bit. And with accurate instrumentation, you can get what's called a light curve, and that light curve can indicate whether there's planets. I'm in a project with Las Cumbres observatories right now, and we are studying and looking at exoplanets and looking for them, and several have already been found. So, and this is like planet hunters type thing. You know, we can go hunting for planets as long as we have a network of observatories to use, and these are all over the world. Okay, so TESS, okay, is instead of a laser point focus looking at one particular star at a time, TESS was looking at thousands at a time and able to determine whether there was planets around them. And the numbers, of course, as you can imagine, would simply skyrocket even more. And now we have the James Webb Space Telescope. Now, if you remember my discussion, here's the visible spectrum: red, orange, yellow, green, blue, indigo, and violet. And I told you James Webb lives out there. Okay, Spitzer was about here. If this is the end of the red that we can see with our eyes, that's the visible spectrum. Then this is where it gets invisible, goes into the infrared. Well, there's far infrared, which is way out there. Okay, way beyond you, Harry, I'm sorry to tell you. Okay, but that particular location is where the James Webb looks. It doesn't look in the visible area of the spectrum at all. It's way out there. Now, what good is that? Well, we'll talk about that. So here's its first light image, all right? And we're on a very fertile planet with lots of dust, aren't we? Yeah, I know. We need windshield wipers for our eyeballs, okay? So the James Webb Space Telescope, it sees light in a way that we've never seen it before. And when we look at a comparison, we can see that in the first iteration of space-borne technology, we had what's called WISE, Wide Infrared Survey Explorer. And WISE had a 1.5 diameter mirror on it, really small. You know, went up into space, deployed, and it was able to look at all these stars and say, oh, look at these stars. Wow, that's cool. We see these nice stars in the infrared. Can't see any details. However, you go from 1.5 feet in diameter to almost 3 feet in diameter, and you get a jump in the resolution. Now, there's a well-known equation to figure that out. The resolution of your camera and your telescope depends on the diameter of your mirror. Well, this 3-foot diameter was the limit for a long time, and the reason is because a rocket couldn't launch anything larger than that, a solid mirror, right? If you wanted something bigger, you were out of luck. Until they devised hexagonal mirrors. And these hexagonal mirrors were put in a network of hexagonal mirrors that folded up and unfurled, basically, once they got in space. And when they did that, they got a 21-foot diameter mirror. And that 21-foot diameter was 100 times more capable than the Hubble. And this is the same scene as this. Look at the difference in resolution. The far right one is James Webb, and the left one, the far left one, is the earliest foray into infrared astronomy. That's incredible. So that kind of thing is something that's amazing. Remember the Hubble shot here? The one on the left is visible light. You can see the dark dust, okay, from whence we came. And on the right is the one that's in the infrared. Now, Hubble's infrared can see out to about here from our visible spectrum. Okay, right about here. Okay, you can't see way out there that James Webb can. So what does the James Webb look like? Well, that's what James Webb looks like. This image is 100 times more detailed than the previous, all right? And the resolution is unspeakably beautiful. You can almost just stare at this for hours. And by the way, on my machine in my office, I have the full resolution image, and the entire screen, which is massive, is about this big. So this object in resolution is incredible. You can zoom in on this and see such detail in here, and by reducing it in size to put it on a thing to show you, it looks like that. But understand that at the resolution that this is, it would be bigger than this whole tent by about 2.5 times, all right? And you could see all the detail in there. Oh, it's just incredible. I can't stop talking about it, so I better just go to the next slide, all right? Now, here's a question for you. We love our science fiction, and we wonder about science fiction and ask, did science fiction contribute to our understanding of alien life, or did it actually, provide some kind of weird interpretation for us on extraterrestrial life? Did we come to an opinion about extraterrestrial life because of it? Let's find out. Now, when we talk about the roles that TV shows and movies play, we have to look at some of the movies, okay? Name the movie. Day the Earth Stood Still. Almost, Joe. Right. That's right. That's very good. It wasn't the one with Keanu Reeves. It was the original. Klaatu, Niktu Baratu, right, or something. Yeah. So and we have to look at the message that these movies delivered. Don't worry, we're getting to the physics. Trust me, I'm warming you up. This movie had a message, and that message was, don't mess with weaponry. If you want to become part of the Galactic Club, you got to watch yourselves, be careful with technology, be good to each other, be kind. It was one of those messages, right? What was the message of this movie? And first of all, what was it? This was the original Alien, and the alien creature was called a xenomorph, if you remember. And xenomorph, from the word of xenophobe, which means hate everything but yourself, basically. And so the message was aliens want to eat your brain, because that's what the alien creature did, right? And it was meant to be a horror movie in space. That's how it was billed. Okay, it worked. First time I saw it, I didn't want to go into my basement. I didn't want to clean the ducts in my furnace, because, I don't want to even see, there's probably a xenomorph in there. I was like, oh, geez. Scared the crap out of me. And I was not, this was, what, oh gosh, I must have been 25 when this came out. I don't know. So I don't mind telling you, the movie scared me, especially and the chest burster, it was called. Now that I do, and I own a company that makes the visual effects stuff. Now that I do all that, I've done some really cool visual effects stuff for people, and it's like, well, now it's sort of interesting to see how these are all done, and I don't get the same kind of scared feeling anymore, because I know it's just an effect. But anyway, so that's Alien. We're going to eat your brain if we ever see you here, okay? How about this movie? Who knows what this one is? Yeah, you got it. He said it, and I heard over there. Prometheus. Huh? Prometheus, yeah. Exactly. And what's the message from Prometheus? Yeah, the message was, yeah, we are the engineers. We created your planet, but you didn't live up to expectations, so we're just going to wipe you out and start over. The message was, Earth is insignificant. Life on Earth is insignificant. we're going to start over. We're just going to wipe you out and start over. I mean, I'd be like, excuse me, you know, I don't think that's a good idea. All right, but that was the message of Prometheus. And then we had this one. Come on, everybody knows this one. Yeah, that's right. E.T. phone home. Elliot, remember that? That was a great movie, you know. And the message there was aliens coming here don't necessarily want to be found. They're benign, and they're vegetarians, and they're also interested in botany. Okay, they're interested in life in general. They worship life. Was one of the most important messages in this movie. They think life is special in the universe, and so they go to planets to study it. And that's kind of in line with what I think, and I'll tell you why. Because in my view, if there's an advanced civilization out there, and they can look any way, I think they might look very different from us. They might be very similar. But let's say they look like E.T. Okay, creatures coming here have already gone through all of the mechanism. Thank you. All the crap. Okay, they will have found the nuclear era. Okay, because every atom in the universe is the same as every other atom of the same type. Okay, hydrogen, no matter where you go. And so when we look at these different elements that are out there, they're all the same everywhere in the universe. So they will have discovered fission, how atoms are so powerful, and when you split atoms and break them apart, you get a lot of energy release. They'll discover that. So they'll have a nuclear era. They'll discover potential fusion. We're getting there now, as you'll see. All right? And they'll discover all the things and have wars just like we do. They'll fight over territory on their planet. But once they free themselves from their world, there's not going to be any need for that stuff anymore. And so what's going to happen is they're going to become, as I think, scientist explorers, because they're going to want to do what we do. Now, why? I said it yesterday in my talk. Every creature on our planet has a characteristic. Do you remember what that characteristic is? Thank you very much. Very good. It's curiosity. Was that you, Harry? Nice. Yeah, it's curiosity. And curiosity is something imbued in every single creature on this planet. All right? Even him or her. Yeah, exactly. Yeah, I don't mind. They're great. Okay? Yeah, we were one once. You know? And so every creature has curiosity. And that curiosity is something that drives it to look. A dog sniffs something. It's not just necessarily a dog saying, food, eat. That happens, sure. But sometimes a dog just wants to know what's over there and sniffs that, you know. What's that smell on you? Tell me. You playing with the cat and not telling me? Yeah? Okay. But the bottom line is that curiosity is something that drives us, and every creature has it. So therefore, we can kind of make an assumption that for carbon-based life like us, which is a carbon bigot, I will promise you, is probably most of the life in the universe, that carbon-based life is going to require oxygen, and it's going to also be imbued with that template provided by the universe of curiosity and DNA. So there's a lot of cascading reasons why life in the universe can exist, sort of like us, but it's all going to come down to carbon-based life like us. Carbon's number 4 on the universe in terms of quantity, 4th most abundant. Oxygen's the 3rd. It's even more plentiful than carbon, as I mentioned yesterday. So there's a lot of reasons to expect there's extraterrestrial life of various different kinds. So engineers trying to come here telling us that we don't match up and that they're going to wipe us out, well, screw them, okay? We need technology to get off the planet, right? So we're getting there. Now, in addition to Prometheus, we had this one, Independence Day, that's right. In this movie, you can get a redneck flying an F-14 right up straight up into an alien ship. Now, that's cool, right? Yeah, that's right. So, and what was the message from Independence Day? Yeah, the message from Independence Day is that even in the face of a deadly alien invasion, we can still prevail. We can figure out a way to get around it. And that may be very true. That might be true. We don't know yet because we haven't really faced any alien invasion yet, have we? Or have we? Yeah, maybe. All right. So, and then, of course, there's this one. Close Encounters of the Third Kind. Yeah. I had the pleasure of working with Douglas Trumbull, who did the special effects in that movie for 10 years. And Doug did 2001: A Space Odyssey, he did Blade Runner, and we were very good friends. And we developed technologies together, we did movies together. And one of the things that was very interesting was he and Jacques Vallée were very good friends. When I found that out, I said, Doug, I'm speaking at the International UFO Congress in 2016. Why don't you come with me? Jacques going to be there. And he went, really? Yeah, okay. Next thing you know, Doug and I are speaking at the International UFO Congress, and Jacques and I and Doug are hanging out. It's like, whoa, it's Jacques Vallée, Doug. He goes, yeah, I know. I was the one that was starstruck because I got to meet Jacques, So the bottom line is that, Close Encounters was fascinating. And then, of course, we had this guy in there, right? J. Allen Hynek, right? Yeah, I hear the thunder as well, by the way. So, we'll keep watching that. So J. Allen Hynek was in there as a cameo, and Doug met him. And he knew J. Allen Hynek, And it's really cool. I never met J. Allen Hynek, Who am I? So anyway, the message from the movies is sometimes messages of survival. It goes up and down, exactly right. We're going to be eaten by an aliens if we ever bring them here, or we're going to learn how to cope with aliens, and we're going to be able to destroy an alien invasion, or we're going to be able to have a benign race visit us. So what's really out there? I'll say this, it's probably all of the above, except for the engineers. I don't want to think that anyone seeded life here and they're just going to say, I'm going to wipe it out, So that said, the question is, why is Earth so visible to alien life? And I kind of alluded to this I talked about it yesterday. Who knows? Yeah, it's blue. That's correct. And what's the blue? Well, the blue, yes. Oxygen, okay, the answer is yes. Earth is very visible to life like this, and it is our pale blue dot, or as my favorite astronomer has said, and I've said this before, the pale blue dot, our planet, our Earth, right? Carl Sagan, right? The pale blue dot speech that he gave, it brings chills the way he talks about it. It's gorgeous. If you haven't listened to it, look it up on Google and listen to Carl Sagan's pale blue dot discussion. It's only like 10 or 12 minutes long, but boy, is it really, really poignant. So that pale blue dot is in part because of oxygen, yes. And the reason is because oxygen scatters the blue light from the incoming star, which is our sun. So does nitrogen, all right? And so that's why the sky is blue. Not today, all right? But that's why it was this morning. It's blue in every direction you look because the molecules in every direction are scattering the blue light in every direction. So everywhere you look, it's blue. And the sun looks yellow, doesn't it? It's not. The sun's actually white. When you go into space, sunlight's actually white. It's because it's looking through some atmosphere that we see it. It looks a little yellow because some of the blue light is taken away out of red, orange, yellow, green, blue, indigo, and violet. And if some of the blue is reduced, more of the red and orange and the yellow show up. So it's an illusion. It's actually a white star, okay? Just out of curiosity. So in any case, we had this great oxidation event. I kind of showed you this slide. I think yesterday you saw it. This is a different talk, same slide. And we had the oxygen level rise up in our atmosphere very, very quickly. Photosynthesis in the oceans allowed oxygen to build up. So it was small creatures that actually created oxygen in our atmosphere, all right? Now, the James Webb can also see this, as I mentioned yesterday. Now, it's worth repeating. The James Webb's looking way out there, but it's looking at collisions between oxygen atoms, and those atoms collision out there show up in the spectrum that James Webb sees. There's nothing in the visible spectrum other than the actual signature of oxygen, and the Hubble could see that. The James Webb can't. It's only looking out there, right? However, oxygen collisions out there show up on the James Webb, so it can infer the level of oxygen in an atmosphere, and that's another thing it's doing. It's also found planets. One thing that's very important about the James Webb, we might have found life with James Webb. Have you heard this? Huh? You are too well-read. That's Harry and his brother Joe. Okay, the thing that's important here is that when we talk about finding life, what we're looking for is the signature of life in the spectrum that we see coming from the region where this planet might be. And that planet, when it passes in front of its star, is going to have a contamination that shows up in the spectrum of the star. And then it'll go away when the planet finishes passing in front of the star. Well, we did see some contamination, and that contamination was of a planet that was around this star, and the compound that was actually seen was something called dimethyl sulfide. And I know you don't know what that means, some of you do, but dimethyl sulfide, you've all heard of it, you all know what it is exactly. Have you ever been to the ocean? Has a tide ever been out and you go, oh, you smell that? That's dimethyl sulfide. Plankton farts. I know that's kind of crude. It's actually the waste product from plankton and other biological creatures, and it's only made by life, only. So when the James Webb found dimethyl sulfide in the atmosphere of this planet, it was like, wow, we might have found life. So they're in the process of confirming it now. But there was too much of it. We couldn't understand why there was so much dimethyl sulfide in this one little planet. Well, it turns out the reason is because it's a water world, and it's covered by water, apparently. There was lots of water seen in the spectrum, so much so that they suspect that it's mostly a water world. And it's going to have tides because it's going to have its star pulling and prodding on the planet's oceans, and that's actually going to cause reduction in size here, increase over here. And if there's land masses, we are going to, small land masses, we are going to get tides, and we're going to get dimethyl sulfide. And we're going to get a proportionally larger amount the bigger the planet is. And so we discovered that the planet's huge compared to the Earth. It's actually called a Hycean world, which means it's got a hydrogen atmosphere. However, the interesting thing about that is even though we can't survive there, apparently some kind of life can, because it's underwater. It doesn't care what the atmosphere is, right? Effectively. So that might be that. Now, if we have this beautiful blue planet, and if we're visible to alien life, the big question is, how can they possibly get here? Well, how can they possibly get here? What kind of leverage, what leverage can they use? Well, it goes to these 4 fundamental forces in quantum physics. This is not a quantum physics class, but I will just share with you very simply. You have the weak force, okay? The weak force is why you're here in that ugly periodic table of the elements that only a couple of us really like, okay, including Sev, okay? The periodic table of the elements is something that shows us all the elements that we know, and we categorize them, and the way it's laid out is very important. That's why it looks so funky. But the weak force is governed by, it governs something called beta decay. Example, turning a helium atom, all right, into a lithium atom, turning a carbon atom into a nitrogen atom. See, it percolates down the table. That's called beta decay. A carbon isotope becomes a nitrogen atom. So it can percolate down and make more elements. So that's what beta decay is. That's what a weak force is. The strong force, that's what holds the atomic nucleus together. And as it turns out, the current calculations, and I say current because you never know, the current calculations show that the size of a nucleus of an atom can be about 118 protons, but not more. Because if you go more than that, it spontaneously decays back to 118. So it looks like 118 is the maximum size. And I think that element's called agnesin. Okay, I told you I do sing the periodic table, and it can go from the first element all the way to 118. I'm not doing it. I don't have time. Otherwise maybe. So the strong force is what keeps the nucleus together. All right, because protons are positively charged, and like the 2 north poles of a magnet, you can't squeeze them together without them moving past. And so the positive protons don't want to go together, but the strong force holds them together. Okay, the last one, or the second to last one, is electromagnetism. Now, electromagnetism is just light. Okay, now light is a combination of electric and magnetic fields, believe it or not. Okay, and they're kind of perpendicular to each other, and they emanate, but don't even worry about that. We don't care. But what's important is all of those previous ones, weak force, strong force, electromagnetism, those can all be described with particles and with waves. That's called duality. And we have that with all of those. And then we have gravity, the weirdo. Okay, gravity's a weirdo. So gravity cannot be described so far with a particle. Now, who remembers what the name of the particle is that we would call a gravity particle? The graviton, right? Graviton. With light, we have photons. With electrons and the weak force and the strong force and protons, we have equations that can describe the wave, all right? And we have particles, the proton and the electron, that we can describe them as. They show properties of both types. And so we see that with everything there, light is a photon or a wave, right? Except gravity. Gravity's the weirdo. It sits outside. We can calculate it. We know the calculation of gravity, F equals GMM over R squared. Okay, the big mass and little mass, like the Earth and the Moon. We can calculate the force of gravity between them. Oh, yeah, I can do that all day long. And by calculating gravity, we've actually accurately left our solar system with Voyager 1 and Voyager 2. We've accurately gone to Mars and put probes down on Mars. We've gone to Pluto and shown Pluto in unprecedented detail. And then actually continued on to an object called Ultima Thule, which is out in the Kuiper Belt, far beyond Pluto. The first look for real at one of those icy objects out there. And by the way, like Oumuamua, it's shaped like a pancake, okay? Which is very interesting, a dual pancake, all right? So they can be, the ability to only calculate the force of gravity, we've done an awful lot of things, all right? We've gone to the moon very accurately. Yes, we did go to the moon. I don't want to hear it, okay? So I don't want to hear anybody say, well, no, we didn't. Kubrick did it. No, he didn't, okay? I can prove that about 5 different ways, okay? So gravity is the weirdo, but one of the things that's very interesting about gravity is that gravity is something that we're now studying with a little bit more care. And one of the things to talk about to study gravity is we need more dimensions to be able to talk about gravity, because maybe gravity exists in more than the X, Y, and Z moving through time, our 4th dimension, than we're in. I'm at an X, Y, and Z coordinate right now at a certain particular time. Now, 1 second later, I'm at this other place. So I have 2 sets of X, Y, and Z moving through time. I'm here, now I'm here. That's the 4 dimensions that we use. Everything we've ever done, everywhere you've ever gone, everyone you ever knew, every object you've flown in to get here, like me, okay, every spacecraft only has done stuff in the 4 dimensions. And we have limitations in the 4 dimensions, especially if we go to space, right? We can't go faster than the speed of light. Now, light is fast. If you could circle it around the Earth, it'd go around the Earth over 7 times in 1 second, okay? The Earth is 25,000 miles in circumference, so that's a lot. However, if you look at adding some new dimensions to this, we might be able to find out where gravity really comes from and how we can use it to do interstellar travel. And that's the thing that's happening now. CERN is doing experiments. Lawrence Livermore is doing experiments. Their experiments and their findings could result in interstellar travel for us, because they're looking outside of our 4 dimensions. This is real science, folks, not science fiction, not woo-woo, not let's all sing Kumbaya. This is real science. Now, Kumbaya might work, I don't know. But this is the real science, and it's only the rigorous application of science that will actually get us off the planet. And so here's where this comes from. So in string theory, we treat particles differently, and the whole point is we need extra dimensions to be able to describe how we can utilize these dimensions to go from here to there or whatever, very, very far away. And the way we can do it is by considering that our X, Y, and Z dimension is actually, X, Y, and Z moving through time, is actually part of a string theory concept. And here's how it works. Hydrogen is a proton with an electron, okay? Here's the proton. Is it just sitting there? No, it's doing this. It's vibrating, all right? Let's suppose you stop a proton at this end of its travel and then stop it at that end of its travel. Now it's gone this far, okay? That little gap between it is the path that it took to go from here to here. Think of that as the string. It's infinitesimally small, all right? But everything that describes that string can be used to describe a proton. You can describe the proton perfectly by making it a string, not a particle. Why? Because that affords us the ability to use these extra dimensions. And one of the theories in string theory is something called Randall syndrome 1. You don't have to remember that. It's RS1. And it's got our X, Y, and Z moving through time, which I've talked about. But it has a fifth dimension. And it actually has a name. It's called the bulk, like bulk produce, B-O-L-K. All right? And that fifth dimension is very important. Then there's another border called the Planck membrane at the other end of that. You don't care about that. But what's important is that we want to get into that fifth dimension, because the fifth dimension is a special place. If we can go from our 4 dimensions and take this water bottle and send it into the fourth dimension, or into the fifth dimension from here, its shape and everything is retained. It gets into the fifth dimension, and the farther in it goes, the smaller the universe around it becomes. Okay? And so if you travel 12 inches out here in the 4 dimensions, you travel 1 through 12 inches, a ruler. Go into this fifth dimension, and you go further in, and now the universe is compressing around you. That same 12 inches of travel that you do in there will be expanded to the actual distance you traveled in that compressed universe. So when you come out, you may have traveled thousands of feet, depending on how far you go in. If you go in an awful lot, that same 12 inches, 12 is an arbitrary number, you know. If you go in 12 inches there, way up high into this fifth dimension bulk, the universe has been compressed so much around you that if you travel 12 inches within there, when you come out, you might have traveled 3 light years. Okay? So, and that's, by the way, without traveling from point A to point B and going through every point in between. You would literally vanish from here and up here over here. Okay? And it doesn't violate any physics. Now that makes you think, well, wait, that sounds like invisibility, cloaking, all of that. It does. And to our eyes, watching this from the 4 dimensions, that's just what it's going to look like. And this is real. This isn't Marc making it up. This is something that's part of Randall syndrome 1. Now, to generate those particles, you need to have a way to do that. And so those particles have a special name. They're called Kaluza-Klein gravitons. Who's heard of KK gravitons? I didn't think so. They were found in the 20s, theorized in the 20s. And guess who's heard of them now? CERN and the Large Hadron Collider. And guess who's generating them and looking for them right now? CERN, the Large Hadron Collider. They added a detector on the Large Hadron Collider called ATLAS, A-T-L-A-S, all caps. ATLAS has been used to study Kaluza-Klein gravitons, or Kaluza-Klein particles in general. And why are they looking for them? Because they're very, very interesting. Because it turns out Kaluza-Klein gravitons don't live in our 4 dimensions, but we can make them in our 4 dimensions. All right? And if we can surround our spacecraft with them, or our ship with them, they live in the 5th dimension. Ta-da! So if you surround your ship with them, you get pulled into the 5th dimension because they're going home. And now, depending on how many you put around your ship effectively, you can find yourself going further and further into this 5th dimension, the universe smaller and smaller around you. Then you can travel some distance in there. And when you come out, you will have leaped to some new spot. Okay? Depending on how far you travel. It may not sound like it, but a Stanford professor calculated that if we went into the 5th dimension to a certain amount, we could actually travel to Alpha Centauri in as little as 20 minutes. Now, with conventional rocketry right now, our earliest we could get there is 10,000 years from now. I think 20 minutes is pretty good. I actually foresee a time where we'll go to Alpha Centauri for lunch. Where were you? I just went to Proxima Centauri with Bob. Had some lunch, came back. What happened since I was gone? Oh, nothing. The kids went to soccer. Oh, cool. I can actually foresee that, you know. And this isn't wishful thinking. This is actually science happening here. So when we talk about the shape of UFOs, they're key because we talked about generating these particles. Well, how do you generate these particles? We noticed that UFOs generally are circular, right? Discs. They're triangular. You can put a disc inside a cylinder, okay, or inside a triangle and a cylinder. So I think they're particle accelerators because that's how we generate these particles. Kaluza-Klein particles are generated with a particle accelerator, like the Large Hadron Collider which is 22 miles in size, 300 feet underground overseas. That's the level of our technology now, not 75 feet or 30 feet like the typical UFO is reported as, right? So that means that if UFOs are particle accelerators, they can emanate these around their outer ring, these particles. And as they do, okay, more and more particles, they will end up being pulled into this fifth dimension. Now, what are the consequences of that? Well, we're going to talk about that.
There is a storm that's approaching us right now that is going to hit in about 10 minutes. It's likely to be here. And so if you have a light camp or anything like that, it might be something that you want to batten down because there is some heavy rain. It appears like just upon us. So we've got about 10 minutes for that to be on us. So once you guys hit the door, you'll see what I'm talking about. But just wanted to give all you guys the heads up right now.
All right. Whatever you got to do. Yeah. Yeah. How do you recover from that? Well, I'm not going anywhere yet. Okay. So, wow. Well, for whoever's left, I will try to finish. So UFOs are probably particle accelerators. They generate these particles and they dispense them, and these ships can be like 30 feet in diameter. Our smallest accelerators are kind of like this one. You can see a little truck down there in the lower right in the asphalt area. And that particular accelerator can do some things, but not a whole lot. The problem is they're trying to constrain high-speed protons in a circle. And when you try to constrain protons to go in a circle, they give off radiation because they don't want to go in a circle. And that radiation is called synchrotron radiation. Well, UFOs and alien races will have figured this out. And they'll have figured out how to deal with synchrotron radiation, I am sure. Okay? So the thing is, once they figure out synchrotron radiation, they will generate these Kaluza-Klein gravitons, which are 10 to the 16th times stronger than our gravitons holding us to our chairs right now. Okay? I know I'm only looking here, but it's over there too, isn't it? And so they're very powerful, and they also generate micro black holes, another construct that we are looking for but haven't really fully proven yet. All right? But it's theoretical. Now, this is the secret to how these UFOs work, and as I mentioned, because what's happening is they surround their ship with these particles. Mini black holes with them, micro black holes. The micro black holes are very important because what would those look like? What would those look like if we actually saw a micro black hole? Yeah, here we go, right? Don't worry, we'll work right through the tornado. It never hits tens. Lightning never strikes poles. Yeah. So what happens is these micro black holes will, what? Yeah. Yeah. See, that's a very important observation because that's something that I can speak to, because everything we observe with, you feel it cold now, okay? So now this is the downdraft from the thunderhead coming at us right now. I wish I didn't know all this stuff, but I do. I'm sorry. Damn. Yeah, so everything we see in the photos, everything that you see with our eyes, color changes, winking in and out, all right? Halos around them. These are all properties that would exist if Kaluza-Klein gravitons are in play. So like Avi Loeb, I say we can't deny the possibility that we're looking at Kaluza-Klein gravitons in play. Can't deny it, yeah. Yeah. Well, what's happening right off the bat is as the ship is generating these particles, okay, it's mediating them away. It's stopping the process, doing far less, all right? so that it can actually come down and make contact with a physical planet, right? And the atmosphere is doing that anyway. So every effect that people are saying, like the auras around it and all that is theoretically possible with Kaluza-Klein gravitons. So as it comes down, it's generating synchrotron radiation, remember? And there might be other forms of radiation it's giving off, possibly Hawking radiation, okay? All these things are very important. And when we look at a ship that's actually generating these types of gravitons, the most important thing is that those micro black holes, besides absorbing a little light and maybe a couple of molecules, and those micro black holes, by the way, last nanoseconds. That's billionths of a second. They come and go, boop, and they're gone. All right, after doing a little job, they grabbed a photon of light. Okay, well, that particular process is something that keeps these particles, these gravitons, all right, as at the forefront. And what will happen is when the micro black holes absorb light and a little atmosphere, they're also absorbing something else that's very important, and that's gravitons that are emanated by the Earth. So it means that the ship itself isn't subject to Earth gravity either. So it's not going to be pulled down to the planet, all right? It'll wink out, it'll go into this fifth dimension and come back at the next low level, wink out and come back at the next low level. It doesn't have thrusters, it doesn't have engines. It just has a particle accelerator to generate all of this activity. That's all it is. Hard to believe, I know, but that's how it can work. So these gravitons will pull the ship into the bulk, and the bulk's highly warped, as I mentioned, so now you're aware of that. So time travel's a little bit messed up inside there, but I'm not going to go into that, all right? But the transition in and out of the bulk has to do with how many gravitons, Kaluza-Klein gravitons, you surround your ship with, okay? That's very important, all right? And nice thing is, everything that, as I said, that is reported visually from UFO sightings, right there, UFOs changing in colors and shimmering, absolutely reported, okay? Overtly vanishing only to reappear, fading in and out. That's all potential evidence of Kaluza-Klein gravitons in play. And this happens all the time in UFO sightings. And when someone approaches a UFO on the ground, as you've heard, they go to touch it, what happens? They get burned. Synchrotron burns. It's synchrotron radiation doing what it does to human flesh, which is not treat it well, not very kindly. All right, it's not ionizing radiation per se, like plutonium, but it's radiation caused by these protons that are being constrained in a 30-foot diameter UFO that are going. The radiation's coming out in all directions except in toward the occupants who are in the middle. They're shielded. When they shut it off, they're vulnerable, which explains why some UFOs can crash. If they shut it off, or if we have a way to disrupt it, it can fall out of the sky because now it's subject to Earth gravity, right? So there's a lot of different things that are going on. And the verdict for me is that they may be producing massive gravitational fields, and that's how they operate. And so when they come here, they're going into the fifth dimension, but they're able to go in really far. And by going in really far, that means that when they travel within that fifth dimension, when they come out, they can have jumped a long, long distance, all right? And so if they're 4 light years away or 25 light years away, doesn't matter. They have the technology to go into the fifth dimension farther and then travel some distance. So a realistic journey might be 14 hours, 12 hours for them to get maybe 50, 100 light years from us or come back. So this is all very real possibility now. And Avi Loeb at Harvard, he actually, as I said, he's a great guy. He actually said, I've been talking about this for about 4 years now. He came out just last year and said that he thinks that maybe they're traveling interdimensionally too. So this isn't just Marc talking, right? This is now Harvard and other people saying this. I love it. The more the better. And the more research, the better, because I may not be right, but I'm never wrong. No, I'm just kidding. All right, so this makes sense. So the question is, where are they hiding? Well, the moon is not hollow, all right? And people say, but it rang like a bell. That says it's hollow. Bells are hollow. Do you know how bells work? Bell's set up a standing wave. When you hit him, okay? A standing wave is set up inside, and it comes out of an opening. The moon doesn't have any openings, okay? And besides, that standing wave is in air. So when you have an impact that strikes the moon, we get a seismic disturbance. If it generates a sound, which is a seismic disturbance, right, it's going to go through the moon and go to the other side, bounce off the other side of the crust, and come back. That's the ring. And why do I know that? Because if you go to Ringing Rock State Park in Pennsylvania, Ringing Rock State Park, they give you a hammer when you go in, all right? And you're encouraged, hit our rocks. And they go, bing. They're all like little anvils. You hit an anvil with a hammer, and it rings. Why? Because the composition is almost the same throughout. And that's what the moon is. The moon is almost the same throughout its composition. That's why it rang like a bell. That was the wrong term to use because everyone thinks bells are hollow. And so when that was made, that statement was erroneously made by whoever said it the very first time. So they're not in the moon, okay? And again, they don't have to be. So the question is, if you want to see the moon and actually see detail, yeah, Roxy? Oh, I know you love the megastructure thing. Okay. Yeah, thank you. Thank you very much, Sadia, for getting away from her now. Okay. I know her very well. In fact, I encourage them to come. New York State, and then, of course, you know where he's from. So the bottom line is that if you want to see the moon in ultimate detail, and you can take a picture of this screen to remind you, Google the LRO quick map, all right? And you, your spouse, boyfriend, or girlfriend will probably break up with you because if you're interested in this stuff, you're going to go exploring the moon in unprecedented detail down to objects that are only about 30 feet across because the Lunar Reconnaissance Orbiter sits 30 or 60 miles above the moon, and it maps in swaths. It's done years of this so far. And what they see is the most incredible detail on the moon, including the tracks left by the rovers, the flag. In some of the cases, when they actually brought it to 30 miles, you can see the flag shadow outside the lunar descent module. And the flag is still standing in some of these landing sites. Right? So there's an awful lot you can do with this. There's so many things. I teach classes on how to use this LRO quick map because it has so many possibilities, so many technical capabilities that people can see things like. People say, craters are all the same depth. Oh, yeah? No, they're not. You can go to the moon, and you can actually use a tool in there, a measuring tool, draw a line across a crater, and it draws a profile of how deep that crater is, and you see it in meters. And then draw one against another crater that's similar, and you'll see that that crater might be more shallow or even deeper. Okay? So the point is, we're looking at a natural satellite. It's not a megastructure. It doesn't have to be. It is odd, and I give Roxy that. It is odd to see a moon that's the size that it is. That's the only moon in our solar system that's the same proportional size to its planet, a similar proportional size. Now, Jupiter has some very large moons. Ganymede is the largest moon in the entire solar system. It's bigger than Mercury, okay, which is a planet. But Ganymede's called a moon because it orbits Jupiter. All right, so anyway, LRO Quick Map will give you all kinds of data on the moon. Enjoy that. So are they hiding in the water? All right, I often say they go where we are not. And, of course, the deep ocean is, I think, where they are. Now, why is that? Because the technique I've been talking about, this process of going into this fifth dimension and back again, there's a way that you can utilize that so that you're neither here nor there. And that's if you move with such a high frequency back and forth between this fifth dimension, okay, that you're not here for any length of time, you're not there for any length of time, you're kind of always in between. So you could be in the deepest part of the ocean and just go take a nap, and your ship will just be going back and forth at idle, all right, the whole time, which is kind of cool. And that process is something that I think they're doing. Now, some of you know the story. Well, I was on a U.S. submarine as a guest. I wasn't even a sailor. I was seasick, as you can imagine. I didn't get sick, but I had to have dinner with the captain because that's kind of what they do. You go on the ship as a guest, and you get to have dinner with the captain. Woo-ah. Well, I was seasick, and I said, I'm not going to be able to eat anything, and it's the best food in the Navy. So I would really be insulting someone if I didn't eat. So I wanted to get my stomach back. I sat next to the guy running the sonar. Okay, 4 sonar stations on this attack submarine. I was at number 2. 1 was active. Ooh, there's a flash. Okay, and at that point, when we had this active sonar, what happened was I was starting to drift off to sleep, trying to get my stomach back, sitting up, because it was off the main alley on the submarine. It's sort of what's called the sonar shack. It's a little alley of consoles. And I'm sitting there, and as I'm drifting off, all of a sudden, the sonar kid on the sonar said, con sonar, fast mover, fast mover. Oh, a torpedo? Why did I go on this trip? I'm going to die out here. I literally was terrified, like instantly terrified. I'm no hero, I can tell you that. So the executive officer kind of saunters around and says, oh, what do you got? And I'm thinking, a little faster, dude. It might be a torpedo. How much time we have? I don't even know. Well, the kid was looking at him, and he was up there looking back at the kid, and I'm over here in station number 2, and the back of his head is toward me. So he says to the XO, the bearing and the range, the angle off the boat and how far. I didn't hear that part. I was too busy thinking I'm about to die. Okay? Well, then the XO said, well, how fast is that moving? Because it came and it was like a transient, then it went. And the kid did a calculation, then he turned sideways in his seat and went like this. He couldn't answer, and he said, sir, several hundred knots, that's several hundred miles an hour underwater. Nothing does that. The Russians have a torpedo called the Skval. It goes 200 knots underwater. It's a steam torpedo. And basically, the torpedo is running into its own vacuum that it created. So it's effectively like the water's not there. But that's the loudest thing in the ocean. It's not a silent, almost silent transient like this was. Okay? So they knew it wasn't a squall because it was moving more than 200 knots. It was upward in the range of 400 to 500 knots underwater, is my guess. Now, I heard that, and the seasickness was gone. It was like, boom, gone. And I actually, the XO turned to the kid and said, okay, log it and dog it. And the kid said, sir, yes, sir. And the kid turned back, and now it's business as usual. And they go, no. And me, Mr. VIP, gets up and, oh, I was a very special person to be on that boat. That's right. You know where this is going. So I walk up to the XO and said, sir, I know what these fast movers are. Is there anything I can help you with? He goes, D'Antonio, right? Sir, yes, sir. You having a good trip so far? Sir, yes, sir. Let's keep it that way. And I went, okay. And I went away, sat back down, and I couldn't wait to get off the boat because I wanted to research these fast-moving underwater objects that they didn't understand. As luck would have it, 2 years later, I did a job for the Joint Chiefs. One of the things I used to do, and still do, is I did presidential briefing models. So the president needed a model of a new submarine concept. They had me build it. I drove it down to Washington. It was classified, the whole 9 yards. And so I brought it down there, and I sat with one of the chiefs, the man in charge of the U.S. Navy, the guy. And my brain was saying, don't say it, don't say it. But my mouth was, my mouth wasn't listening. And my mouth spit out, before I could even think about it, can you tell me about the fast mover program, sir? And I literally slapped my face. It hurt. I slapped my face so hard, and I closed my eyes like, oh, God, I can't believe I said that. And he laughed. He goes, no, Mark, I can't talk about that program. I'm sorry. I go, it's okay. No problem. Whoa. I'm thinking, this is real. And it's true. Navies do see these. And I talked to a lot of submariners since then, as I never was one, okay? But I talked to a lot of submariners, and one guy said, oh, yeah, we called them jellyfish on our boat. Jellyfish? Oh, yeah. We didn't have a way of classifying them because there was nothing we could do. They're well outside our understanding. I went, wow. So I ended up finding out that a lot of navies around the world see these objects, fast movers, and nobody knows what they are. And the official role of the Navy is to observe and do not engage. Well, they should have told some of the folks that were seeing these. All right, the Kitsukawa Maru was a Japanese freighter in 1957, and they saw objects rising out of the sea and going into the sea. And the captain had the presence of mind to copy down the latitude and longitude exactly for where they were. And if you put that in, It's right at the bottom of the Marianas Trench, the deepest part of our ocean. Coincidence? I don't know, right? And then in 1963, there were submarine maneuvers off Puerto Rico, and there was a bunch of submarines, 5 subs, and they were in this battle group. And one of them picked up something, and it started to deviate because they didn't know. They thought this was part of their battle group strategy. They didn't know. They don't tell you what enemies you're going to see or what tests you're going to do. So they started chasing this thing. It went full ocean depth up to the surface at ungodly rates, and it allowed them to catch up, and then boom, it would disappear miles away in just split seconds. Sound familiar? Sounds like the fast movers, doesn't it? So that technology is not that far away for us. We're getting there. It's pretty cool. All right. So I do believe that they're here. Now, this is the slide that I like very much because it signals the end of my talk almost. Not quite. But you may remember this television show. Remember what it was called? People of Earth. All right. And of course we had Jeff, we had Kurt, and we had Don. Jeff was the gray, Kurt was the reptilian, and Don was the Nordic. Okay. And it was a funny show. It lasted only 1 season, but it was a blast. All right. But the question is, are they here? And in my view, I think they are. Remember the oxygen? For 2 billion years, we've been putting that signal out to the universe. And carbon-based beings rely on oxygen. All of them. Every one of them on Earth. So oxygen is very important. That's right there. All right. So maybe you're one of them. All right? Maybe. And maybe not. And it's a perfect time for me to end my talk. Right? So thank you. And you may have to yell to ask questions, but I'm willing to take questions. Joe. How do you what? Oh, yeah. Good. He says, how would you navigate those craft? Well, first of all, I can't profess to know because I've never been able to drive one, but I will say this. Here's what I believe. I believe that aliens that use this technology are the best map makers or cartographers in the universe. They know every single entry point they're going to go to. They know there's not a star there. There's not an asteroid or a planet. Okay? So they're very smart about this. They have mapped out ahead of time the regions you want to go where they're going to just pop into existence. Now, when they're traveling in space, there's nothing there. Maybe a few atoms of a few, like sodium, and maybe an oxygen atom or something, or hydrogen most likely. But those atoms will be few and far between, and when they materialize where they are, they're going to displace them immediately. When they materialize underwater, okay, at a new spot, they're pushing water out of the way every moment they do that. And as they do that, they make a sonar signature. And we'll actually see that sonar signature, and that's what we see in our 4 dimensions. Right? So that's pretty cool. Others? Yeah.
If you're going from one point to the next, and you've got a planet in the way, then how do you just go through the whole planet?
You don't go through it. That's the whole point. You disappear from this point, and you appear here. Here's an example. How many times have you heard people say that aliens came through the window of my house, right? How can they possibly do that? You would think maybe, are they going through glass? No, they can't do that. What they do is they vanish from outside your window, go into the 5th dimension, and pop into this coordinate inside your house. You know? And I have a family member that wouldn't stop, complaining about the fact that he didn't want to sleep in his bed. And what he said was that he was afraid the aliens were going to come through his window and take him again. Yeah. So, and coming through the window is something that they can do just by materializing and disappearing from outside and appearing inside. Sounds like science fiction, but in the context of string theory and Randall Sundrum 1 and the ability of you to pop in and out and generate enough energy to generate these Kaluza-Klein particles, it's well within the realm of understanding. Now, I didn't cover this, but how do we generate that energy? I mentioned Lawrence Livermore. I mentioned CERN. Okay, CERN overseas. What is CERN doing? CERN is looking at and exploring these Kaluza-Klein particles. What is Lawrence Livermore doing? Well, Lawrence Livermore is over here. What are they doing? Lawrence Livermore is studying fusion. And it turns out that in order to generate the power required to run an accelerator in a small craft, you need a fusion reactor. Fusion is our next logical technological step. Fission's deadly, right? Fukushima, Chernobyl, 3 Mile Island, right? Yeah, Back to the Future. But that was Mr. Fusion. But if you think about it, fission is like being in a deep valley, okay? In order to stop a fission reaction, which is elements in a fuel rod are reacting with other uranium elements in another fuel rod that's adjacent, and they're sending out all these high energy particles. And if you have exposure to all of those fuel particles in the elements, the little cylinders like this, if all those fuel elements can interact with each other, you're going to get an awful lot of reaction. So you better have a lot of water to cool them, or like lithium, get a lithium coolant or whatever. Bottom line is, if you don't have that, all right, then you've got to use the ability to, if you have water, that's fine, but if you got to shut that reaction down somehow. And so they lower these control rods down in between the fuel rods. And these control rods take energy to put down. And if anything happens, like warping of any kind of the structure or the core, the control rod might not go down. And now the reactor is going to run away. That's what happened at Fukushima. That's what almost happened at 3 Mile Island. And that is what happened at Chernobyl. Okay? That process is how we control a nuclear reaction. If we can't control it, we're going to irradiate a massive amount of land around us. Fukushima, 5,000 square miles were irradiated by this explosive event that occurred. You can see the shock wave when the building explodes. And so in order to alleviate that, we don't want to use fission because we're going to put those fuel rods in to climb out of this deep valley of fission. But with fusion, it's exactly the opposite. With fusion, we're teetering on the brink of shutting off at all times. And it takes energy to maintain the reaction. If you don't put energy in, it stops. And the other thing is, the fuel for fusion, one of the fuels is tritium, all right? Helium-3 and tritium. Tritium is a hydrogen atom with a few extra neutrons. Now, if you rub powdered tritium, it's radioactive, but if you rub it on your arm or you inhale it, oh no, radioactive tritium in my lungs. Guess what? You will excrete it when you go to the bathroom. It's not cumulative like a plutonium is. It will not destroy you as long as you don't keep doing it. No more tritium bread, okay? Don't eat tritium anymore. All right, but the bottom line is that tritium is radioactive, but it doesn't accumulate in your body, and that makes a much safer fusion fuel. All right, so fusion is where we have to go next, and we get the fusion. So you marry Lawrence Livermore to CERN, and they'll live happily ever after, and they'll be able to go planet to planet. I do foresee a day when you could say, honey, I'm going to go to Pluto for lunch with Bob, like I mentioned before, and we'll be back to watch the game tonight. Okay, have fun. All right, we will. We're going to hang out on Pluto's moon Charon for a while, and then we'll be back. So that kind of process is far off for us living now. But in 50 to 100 years, that might actually be the norm. And of course, we know how that's going to work. Only the wealthy can do it first. Yeah, I get it. But it's going to eventually be expanded to everyone because it's going to have to be. Because sooner or later, our sun's going to die. Don't worry. It's about 5 billion years. Okay, with a B. So, and when that happens, we will have had to have left this planet. Because long before it actually does die, the signs of it dying, probably after 4 billion years from now, are going to be that it's going to start swelling into a red giant and start pulsating. And that's going to probably boil our oceans away, kill life on Earth if there's any left. Because we're not going to take every microbe and animal with us, right? But we'll be off Earth. We'll be off planet by then. And Earth might be a distant memory for an awful lot of beings on the planet at that point. So we're going to spread to the universe, and then we will be able to use this technology. This is the only way it works. This is it. Yeah.
Do you have like any theories on how like carbon life would react or survive the shrinking universe?
Oh, yeah, actually, when you're inside the ship and you have the gravitons around you, you're effectively shielded. Yeah, and now if you stopped producing those gravitons while in that fifth dimension, you'd be blasted to smithereens. Okay, but because there's a lot of energy that's expended in that process. But if you can keep them around your ship, right? In other words, have a perfected fusion technology to keep you generating these particles time after time, moment to moment, then you wouldn't have that problem. Now, what would you see? You know how we talk about UFOs? They travel through the sky, they go ding, 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 and they make all these moves, and people say, well, no being could survive that. You're right. Not even them. They're not moving from here to there. They're going ding, 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 ding. All that's changing from them is the scenery outside their window. It would feel just like it does here. That's all. They're moving from coordinate to coordinate. They're not moving through space. It's the hardest concept of this day. They're just moving from one XYZ coordinate at a particular time to the next one, to the next one, to this one, or to that one, or that one, right after that. And all that's changing is the scenery. And that's it, right? So hopefully this talk gave you some ideas about what is in store for us moving forward. I think that I know it's raining and it's probably your captive audience now, I'm sorry. Yeah, haha, now I'm going to talk about the other stuff I don't want you to yeah. But the bottom line is really that this technology is coming. You know, if CERN can study the Kaluza-Klein particle, and if you want to, look up Kaluza, K-A-L-U-Z-A, and Klein, K-L-E-I-N, and then put the next word in, CERN, C-E-R-N, and you can read yourself the white paper that they've written about it, talking about this. This isn't just me making this stuff up, okay? It's on their CERN website right now. So it's really fascinating stuff to see. And if you look up Kaluza-Klein hypothesis in Wikipedia, a lot of it's going to go over your head because you're not getting explained through Wikipedia. Wikipedia is good for some things, really bad at others. This is one of those things where it's accurate, but it's not written in a way that everybody can understand, you know. So that's the only thing to worry about there. But you do have data on this that you can see. There's all kinds of information out there that you can see and find on these Kaluza-Klein particles, Kaluza-Klein gravitons. They're affectionately known as KK gravitons. Okay. So that said, hopefully you thought this was worth it. Excellent. I'm glad you did. Thank you. And the thunder seems to agree with you. Okay. Yeah. If anyone wants to, yeah, right. Thunder. Oh. Trey will have to answer to that. That's very funny. I'll tell Trey Hudson I got thunderous applause. And he'll say, what, really? Thunderous applause, Trey. It was obvious. They applauded and thunder. Well, thank you, guys. If you have any questions, I'm still here for, obviously, till the rain stops. Thank you, guys.